the Coast Mountain Range of British Columbia. 1,000 miles of vast chasms, towering walls, and ice-crowned peaks. Wendy Robinson lives and works in this extreme environment.
It's an incredible place to be. I myself am definitely a mountain enthusiast, so I love this location, whether it's winter or summer. Especially on a day like today, right? It's gorgeous bluebird, you've got the clouds rolling in and out. It's probably the best place on earth. But we're on the coastal range, so we do have constantly changing conditions. Extreme winds, extreme weather, you do get a lot of snowfall. Right now, I think we're sitting at about 9 meters of snow fall this year, with more to come. And so snow is definitely a factor.
It's an environment that humans have been trying to conquer since the beginning of time. Man has often happily lived side by side with snow. But when you add mountains to the situation, survival becomes a lot more difficult. Getting from A to B is a nightmare. There are hazards everywhere. And even if you manage to build a home there, keeping it is far from straightforward. But there's one place where engineers are taking on all these challenges on an unprecedented scale. This is Whistler, British Columbia's most famous mountain.
This pretty much scores at the top of the list for challenging sites.
It's not just the snow, it's any time that you're working at the top of a mountain, you have to deal with wind, rain, lightning. We can get hail. It makes it very difficult to build in this environment.
Whistler has among the highest snow loads in the country. It takes a certain type of engineering and construction method to build in a town like this.
Conquering Whistler requires impossible engineering. Mega muscle in the air. And pure power on the ground. Engineering that goes with a bang. And technology that defies nature.
So Whistler Blackcomb, we're always trying to stay as innovative and ahead of the curve with what we do. This is by far the most extreme project I've ever worked on.
Whistler is the biggest and busiest ski area in North America. It has a record-breaking cable car with an unsupported span stretching a staggering 4.4 kilometers. And the highest altitude suspension bridge in North America.
We're at the peak of Whistler Mountain, 2,200 meters at the very top, so the top of the Whistler Peak Express Chair and above everything. It definitely takes a lot to build in an environment like this with the conditions that we deal with, but when it comes down to it, this is probably one of the best places on Earth.
When you're fighting nature on this scale, ordinary engineering just isn't enough.
Pretty remote and hardly accessible, so how would you get a land crane up there? You'd have to build a road. You guys all set for me down there?
Me and my crew are just on our way, and we'll be about 10 minutes or so.
Yeah, you bet. We'll wait for you.
Copy that. Thanks, Ken.
Jeff Van Driel is one of British Columbia's Avalanche technicians.
So we're driving on Highway 99 here. This section is known locally as the Duffy Lake Road. I think a lot of people think of snow as being this soft, fluffy material, but avalanches have a significant amount of power and enough to destroy vehicles, to destroy trees, destroy buildings. They are a force of nature to be reckoned with for sure.
Avalanches have ripped through this landscape since time began, wreaking havoc and taking lives. Stopping them is impossible.
We are not going to be able to stop the avalanches. They are going to run one way or another. The worst case scenario would be that uncontrolled avalanches would hit the highway. Our job is to maintain the safety of the road and keep it open.
To help Jeff and his colleagues take control of one of nature's wildest and most destructive phenomena, they'll have to draw inspiration from the early pioneering mountain engineers. Mechanical engineer Dan Dickrell is in Flagstaff, Arizona, exploring a solution that came out of left field.
Are you ready? All right, here we go. That was a little high. So the game of baseball is a pretty old game, and the game itself is unchanged since the late 1890s, basically. What's interesting is the technology that surrounds baseball has evolved, though. So what we're doing right now is having a bit of batting practice. As the afternoon wears on, the accuracy of my pitches slowly deteriorates, but we use technology to enhance this practicing experience and take a little load off this old arm of mine. All right, here we go. Ooh, that was a good one.
In the 1950s, baseball practice changed forever with the invention of the pneumatic pitching machine. Finally, human pitchers could take a rest.
This particular machine would be the grandchild of the original pneumatic pitching machine. I'm gonna take this baseball and I'm gonna drop it in. As I do, the compressor builds up air pressure in here. Once it hits a pressure that is sufficient to give me the exit speed that I want, all of that stored up air will be dumped into this barrel, forcing the baseball out and propelling it down towards the batters.
But one man saw the potential for this technology to be used in an altogether different way. Monty Atwater had tried various methods of setting off controlled avalanches, including artillery and dynamite blasting. But after seeing a pneumatic baseball pitching machine in action, he had a brainwave.
Oh, check this out.
This is Monty Atwater's Avalauncher, one of the last remaining examples of his literally groundbreaking idea.
If we look at it, we see this vessel here. This is where the compressed air goes. An air compressor gets hooked into this, pumping air in, pressurizing it, building up that charge.
Instead of firing baseballs, Monty's Avalauncher packs a much bigger punch.
So I've got my explosive projectile. It's got some stabilizing fins, a remote detonator, and then I would drop it in, and then we would trigger it. Projectile would shoot out. Ultimately, when it landed, it would detonate and hopefully trigger an avalanche. Now, the reason why this barrel is so long is because the longer the barrel, the higher the velocity of the projectile coming out. The higher the velocity, the further distance, the bigger the range that you'll have for this avalauncher.
This pneumatic-powered launcher was capable of firing explosive projectiles a whopping 370 meters into a mountain, starting avalanches from a safe distance.
This was a great solution to that problem of how do you trigger an avalanche without putting the people that work on the mountain in danger themselves.
All over the world, new generations of avalaunchers are used to set off controlled avalanches from a distance, and so reduce the chance of a catastrophic disaster. But high up in the mountains surrounding Whistler in British Columbia, Avalanche teams need engineering on a whole new level.
Well, this is my office. It's a beautiful place to work, that's for sure.
Jeff Van Driel is in charge of a new detonation system that pioneering Monty Atwater could have only dreamed of.
What do we got for temperatures up here?
I think we're looking at -2 right now.
The consequences of an unexpected avalanche up here could be disastrous.
As we approach Blowdown Peak, path 51 here, you just see the road is just a sitting duck right underneath of it. And so our job here is to maintain an open highway by controlling the avalanches so that we can control when people are exposed to the avalanche problem.
But the 21st century solution has risen to new heights.
We're at about 2,300 meters, and what we're looking at here is the solution to our avalanche problem. Yeah, Ken, so if you want to just bring us right up to the summit there.
Front of the shack there?
Yeah, that's perfect.
Okay, perfect. Yeah, I'll plan to make an approach. I think should be no problem setting us down on the peak here.
So these are our remote avalanche control system exploders. This is one of our key solutions to keeping the road open from avalanches. This here is the #1 exploder within our remote avalanche control system up here at the top of Blowdown Peak.
These huge spouts are the latest in avalanche management technology, known to Jeff and his team simply as exploders.
So what this does is sends a directional shockwave onto the slope. There's no actual projectile that will end up on the slope, littering the slope or anything like that. It's literally just a shockwave that stresses the snow and initiates the avalanche.
Huge metal tube-like structures called exploders are installed permanently into the mountain face. And not far away is a shelter housing canisters of oxygen and propane. Through a series of pipes, these exploders are fed a mixture of the two gases, which, once combined in the tube, are ignited by a spark. The resulting blast is expelled at great force out of the directional nozzle onto the snowpack. And if the conditions are right, this will initiate the snowslide. Now the team are able to set off explosions from much further away than an avalauncher. By using radio communication, they can retreat to an extraordinary 25-kilometer distance.
Okay, connecting to the west rib. Fire in the hole.
When the risk is highest, the team temporarily closes the road and an avalanche is triggered. They can then clear the debris and reopen the road quickly and safely.
Having this technology at our disposal definitely does save lives. It allows us to bring down the avalanches when we have closed the road rather than avalanches coming down and hitting the traveling public on the highway.
But runaway snow is not the only potential deadly hazard. What happens when all that snow melts? Danger lurks in one of Whistler's most picturesque locations.
This is beautiful Fitzsimmons Creek. This area was glaciated up until 10,000 years ago. The glaciers melted and they left a landscape littered with debris, and it was poorly forested at that time.
Mike Curry is part of the team tasked with protecting the town from the potential devastation a flood through here could cause.
We have these events that come down the creek that are akin to channelized landslides, or we call them debris floods or sometimes debris flows. If we had such an event, if we were to look up the creek, you'd probably see a frontal wave coming down with big boulders and trees, and it would be kind of coming like a bulldozer down the channel, like a small landslide. And in behind it would be a very turbulent, rocky flow with boulders and logs sticking out of it. It would be chaos.
A debris flood on this scale could rip through the town below. So Mike and his team have devised an epic engineering solution.
So this is the Fitzsimmons Creek debris barrier, the largest of its type in British Columbia. We're way above the creek here, as you can see, and you get a better appreciation for the size of these steel members here. They're very, very large. And the way the structure works is that the boulders and trees that can come down from the creek, they hit the steel pieces there, and the load gets transmitted into the two compression pieces on either side. So each one of those steel beams on the left there is a compression beam that is transmitting the load from the creek boulder impact into the abutment over there. And similarly on the other side here, we have a similar situation going directly to bedrock. It's designed that it will bend but not break during that kind of debris flow loading.
Protecting Whistler from a 1 in 2,500 year chance of a debris flood, the suspended steel barricade design is the only one of its type in the world. Perched above the creek, the 8-meter high debris barrier is capable of restraining 34,000 cubic meters of debris.
We have a heavy steel structure here. It's designed to take a hit from a 1 meter size boulder that's moving at 5 meters per second. And they also have to take a 1.5 meter diameter tree that's traveling down with the flood flow and hitting it like a battering ram.
The town can rest easy, safe in the knowledge that the Fitzsimmons Creek debris barrier will protect them if ever an extreme debris flood should occur.
When it's raining in Whistler and I'm visiting, as I often do, I definitely sleep better in my hotel bed at night knowing that the structure is here.
The Whistler region's most famous and popular peaks are Whistler Mountain itself and the neighbouring Blackcomb Mountain. More than 6 kilometres apart as the crow flies, getting from one peak to another could mean a long and time-consuming journey. But engineers have come up with an extraordinary solution. The peak-to-peak gondola. A world record-breaking piece of mountain engineering.
Be very careful and do not cross these lines.
Wayne Wiltsey has the job of looking after this mechanical giant.
So right now we're at the exit of the Whistler terminal and the cabins are heading off towards Blackcomb.
The peak-to-peak spans 4.4 kilometres, nearly 4 times the length of the Sydney Harbour Bridge. At its highest point, it is 436 metres above the ground. That's almost enough space to fit the entire Empire State Building. To achieve this groundbreaking piece of engineering, 4 giant towers were constructed on the sides of the valley. And on each peak, they built a station containing enough engineering might to pull 28 gondolas, each containing 28 people, across a more than 4-kilometre gap.
That's the main drive bow wheel. These 2 wheels are guides. And why they have the 3 is to spread everything out so that we can get the large gauge that's required for the big cabin. Because of the size of the lift, we have emergency brakes or bow wheel brakes on all 3 wheels.
It would take a 2-year build to create the longest unsupported span aerial ropeway in the world.
So right now we're in the Whistler terminal, the peak to peak. It's prior to public operation. We're going to take off and we're going to run across probably at about 6 meters a second. It'll take us about 15 minutes to make the journey across to Blackcomb.
Most cable cars carry their cabins on a single moving cable. This haul rope is supported by a series of towers and loops around the drive wheel at each end of the journey. But take away the towers, and the cable is straight away put under extra stress. And in Whistler, the team are attempting to go further than ever before.
We're spanning the distance between two mountains. With one cable, with just a haul rope, it wouldn't be possible because the haul rope would not be able to support the load of the cabins.
The engineer's solution was a 3-cable system on an unheard of scale. Cables, each weighing around 90 tons, were produced in Europe and brought to site using specialist heavy lift transport. It took 11 weeks to stretch the cables across the valley. Each cabin runs on wheels along 2 static cables, pulled by a 3rd moving cable that operates in an enormous 9-kilometer loop. The 2 highly tensioned static tramway cables provide strength and stability in powerful mountain winds.
You know, think of them as tracks. Think of them as a railway, right? So those tracks support and the cabins ride on the tracks, and the haul rope, which runs down the middle, pulls the cabins on the tracks from terminal to terminal. They were able to, with the track ropes, achieve the huge span. So the span between towers 2 and 3 is just over 3 kilometers in length. At the time, the longest unsupported span in the world.
The result is mountain engineering on an epic scale. A unique achievement in construction once thought impossible.
When you go and you actually look through the floor or you look out the windows, it's kind of like flying in an airplane or in a helicopter. It's a pretty cool experience. There aren't any lifts like this in the world.
Building anywhere in Whistler means overcoming a host of extreme natural obstacles, even in the valley below.
Whistler has among the highest snow loads in the country, a country that sees a lot of snow to begin with.
Eric Karsh is one of the team behind building the Audain Art Museum, a huge new building that will need to cope with 7 meters of heavy snow each winter.
If you ignore the amount of snow that we have here, structurally, of course, it could collapse. Victoria, not far from here, is a town where we had a snowfall that exceeded expectation, and a number of buildings actually did collapse. From the point of view of snow masses freezing and thawing and expanding as it freezes, could literally split buildings in half if you don't account for it. So, yes, it's a somewhat dangerous environment.
So how do you create a building that can withstand the full force of Whistler's snowfall? It's a challenge that might be impossible without the great pioneers of the past. Mount Hood, Oregon. A permanently snow-covered peak blighted by blizzards. How anyone can construct a building to withstand this wild environment is mind-boggling. But structural engineer Nathan Ingraffia is searching through the whiteout for the answer.
We're up above 6,000 feet up the side of Mount Hood. Visibility is maybe 100 yards. It's a really formidable, hostile environment. It makes a snowcat about the only way for us to get around. We're getting close. So this area of Mount Hood, it's not unusual to get upwards of 20 feet of snow in a season, maybe 30. That's plenty of snow to easily collapse your typical roof structure. So you can imagine that designing a structure in these conditions is incredibly difficult.
Daring to build in this most unforgiving of locations was prominent architect Gilbert Stanley Underwood. His mission was to erect a hotel to withstand the impact of devastating snowstorms.
Hey, Matt, you could stop here. It's a good view.
What he came up with was the stunning Timberline Lodge. One of the most extraordinary and unmistakable hotels in the world.
This building has a really iconic shape, especially looking at it from the outside here, from the snowcat. It's really, really a unique design.
Immortalized as the facade of the menacing Outlook Hotel in Stanley Kubrick's film The Shining, Timberline is instantly recognizable thanks to its unique roofline.
The space above me is created by the main exterior structural roof, which is used to shed the snow. It's a tight squeeze.
Just like in Whistler, Underwood needed to create a large building with lots of open public areas that could handle the heavy snowfall.
This is an incredible space to be in.
The answer was a roof design called a cat slide.
So this model represents your typical steeply sloped roof. Just to demonstrate how effective this steep roof is at shedding snow. So you can see that this roof is very, very effective at shedding the snow. Now, if you wanted to make the building larger, to compensate for that, you would lower the pitch of the roof. So you can see with this shallower pitched roof that the roof collapsed under the weight of the snow that didn't easily shed off the roof. The way to solve this problem is the cat slide roof. To do this, we're going to have to lose a little bit of the upper floor area. And now using a cat slide roof, the roof extends past this initial eave height all the way down to a second floor, if you will. Now using another identical bucket, you can see that that roof effectively shed all of the snow and no snow at all stayed on the roof. All of that snow that's shed off is now piled up just outside the building.
The ambitious 55,000 square foot Timberline Lodge finished construction in 1938. And its iconic cat slide roofs were the perfect solution to eliminating serious snow loads.
The concept is somewhat ingenious because it allows you to shed snow while also maintaining as much floor area as possible. Perhaps the only disadvantage here is that we no longer have the view out the window that we might have otherwise, but we've preserved the structural safety of the roof.
Just like the Timberline Lodge in Oregon, it is the Art Museum's clever roof structure that protects it against Whistler's crushing, destructive snow.
So we decided to have this really steep roof and a slippery metal roofing that allows the snow to slip and shed. And as you can see right now, there's no snow at all on the roof.
Like the hotel on Mount Hood, the roofline continues much further than in a traditional building.
That, from a volume design point of view, gives us a space in the middle of the volume that is quite high, where we can have a two-story space. And if you extend the roof beyond that two-story space, you end up with a one-story volume, which is the corridor that we're walking through right now, with a beautiful view to the forest. This way, you can maximize your floor area within that design. So we're in the mechanical well, which gives us a view of the roof from above. So if you look at the roof surface from the top to the bottom, you don't see any joints in the metal elements, which allows the snow to slip off unobstructed because the sheet metal is completely continuous from one end of the roof to the other.
The result is a cutting-edge art museum that can withstand 7 meters of annual snowfall.
It's been my most challenging, exciting project. To build in a town like Whistler, you can't be afraid of challenges. It's not the easiest place to build, but these challenges certainly made it an exciting project.
Our company exclusively works in remote locations. We work all over Western Canada in some of the most rugged, extreme environments that exist. And this pretty much scores at the top of the list for challenging sites.
Ryan Foster is one of the team that must conquer the mountain.
You know, we need to look at this and say, okay, how do we build a structure in this environment? This location is one of a kind. It's almost like standing on top of a pyramid.
The Cloudraker Sky Bridge and Raven's Eye viewing platform will be 2,200 meters above sea level. The highest altitude suspension bridge in North America. It's a design that requires tons of steel and concrete placed on the peak with pinpoint accuracy. But out in the wilderness, traditional construction methods are totally impossible. The solution is extreme air power.
So you can see he's coming in with the log.
The massive Kamov Ka-32 helicopter is designed to be a flying crane, capable of lifting extraordinary weights with ease.
He's got a bubble window, he's looking down. He's gonna bring it in and put it exactly where he wants it off the road. And he'll be placing it right now. Now he'll release the grapple, open up the claws with the arms and fly away. Go for another turn. You need to be very precise.
Shane Palmer is in charge of a fleet of these monsters, and they hold the key to building on Whistler's mountaintop.
So the helicopter's gonna be landing shortly. They're almost down to a fuel level where they have to refuel. I can feel the power right now.
The secret of its lifting power is the twin set of rotors.
The intake there of the engine, there's 2,200 horsepower right there. 44 altogether. The top set is going one way and the bottom set's going another way. So they have counter torque. That's why they don't need a tail rotor. The way you yaw is they change the pitch of the top set differentially from the bottom set.
The two counter-rotating sets of rotors means the Kamov doesn't need a tail rotor to stop the helicopter body from spinning. So every single horsepower is dedicated to lift.
Hang on. Get a thumbs up there. Everything's looking good.
The Kamov can lift up to 5 metric tons in one go, making it the perfect machine for an impossible challenge. Like building the highest altitude suspension bridge in North America.
So when we're erecting this steel, we're 100% working at height. There are 1,703 pieces of steel to connect. These are extremely heavy pieces of steel.
In Whistler, the Kamov and other heavy lift helicopters allow engineers to build at almost 2,200 meters above sea level.
There's over 95,000 kilos of structural steel, reinforcing steel, and anchor bars. And so that requires a lot of foresight and a very careful plan.
The result is record-breaking mountain engineering. The 130-meter Cloudraker Sky Bridge and the Raven's Eye viewing platform.
It seemed like an impossible endeavor. Incredible piece of engineering that's gone into this. Walking out there, the bridge is a incredible experience to walk through with the metal grate so you can see through to the Whistler Bowl below, and then getting out onto that cantilever. I mean, you're sitting out 13.5 meters off the rock, off the cliff face, and looking down into snow and ice. It's an incredible experience.
While many of the challenges facing engineers in Whistler are to do with too much snow, sometimes the problem is down to not having enough.
You know, we have a pretty amazing area that we live in. Lots of steep slopes. Whistler's renowned for its steep slopes. And everybody, as they're skiing it through the day, they push the snow downhill, they push it to the side, and they build huge moguls.
The uneven movement of the snow can spell danger. Ramps can form and rocks can become exposed. The obvious solution is to use a snowcat to push the snow to where it's needed. But some of Whistler's slopes are so steep that an ordinary snowcat would end up sliding off the mountainside.
Oh yeah, it's a battle against gravity. Maintaining slopes this steep is a challenging job.
On Vancouver Island, off Canada's west coast, mechanical engineer Agnes d'Entremont is searching amongst the remains of the once booming logging industry for one of the last surviving examples of an innovation that could help the team in Whistler.
This is a temperate rainforest that grows some of the largest trees in the world: Douglas fir, Sitka spruce, western red cedar. These trees were used for millennia by First Nations, but logging really got into gear when Europeans arrived, who built mills like this to process the logs into lumber. The challenge was getting those logs out of the forest, off the slopes, in order to bring them here to be processed.
Moving monster trees required a monster machine. This is a steam donkey. A mechanical beast of burden with unprecedented power.
This is so rare.
Invented by logging entrepreneur John Dolbear in 1881, this steam-powered winch needed a skilled team to operate it.
Grab a chuck of wood there and chuck it in the fire.
Okay.
The donkey puncher running the engine.
Yeah, there you go.
The spark chaser to put out fires.
Wow, you can feel how hot this is.
And the whistle punk relaying signals to the choke setters who attach the logs.
Right. There you go. There.
Together, they could tackle jobs previously thought impossible.
Off we go, Joe. So right now, the logs are being lifted and dragged at the same time by the steam donkey.
But the steam donkey had a perhaps even more extraordinary skill, one that could hold the key to taming the snow slopes in Whistler.
It's incredible that a nearly 100-year-old machine can haul all of these logs. That's not all it can do. It can also haul itself, including to steeper and steeper slopes. And so to do that, they attach the cable around a distant tree and use the winch to haul this giant iron machine on these enormous wooden sleds up the slope.
Using the muscle of the winch allowed the steam donkey to go where no machine had gone before, transforming the logging industry and taming the forest slopes.
This is the office, and it never really gets old.
On the treacherous snow slopes of Whistler, it's modern winch power that holds the key.
Okay, away we go.
This is the Winch Cat. A snowcat with an added hydraulic winch on a 360-degree turret. It's the ultimate off-road vehicle.
If we didn't have the winch, we'd probably doing about 50 or 60 kilometers an hour about now. Like, we'd be going really fast. Conditions like this, there's just not enough traction to hold up the machine. The snow would just shear off and you'd slide.
A steel cable over a kilometre long allows the vehicle to virtually dangle down extreme slopes and move snow exactly where the operator wants it.
Like right now, I have 3 tons of tension holding us back. The technology and what it enables you to do with the machine, it's quite something. What we have to do here, you can see that there's rock showing in the slope that has to be repaired. The boom is now over the cab, which is why it had that shape, so that we can see the rope in front of us as we're going uphill. So right now we're about 700 meters from where we hooked up the rope. You can see the rope in front of us way up in the air. And we are at 29.3 degrees. Pretty incredible, actually. The tracks are starting to slip now. This is a job that would be impossible with a regular snowcat.
Whistler might be one of the most challenging environments on the planet, but engineers refuse to let this world of snow and ice beat them.
You're missing out if you don't take at least one moment every day and do a 360, as this is extremely special.
It's a real privilege to be able to work with this type of technology. It's really spectacular, and I really enjoy my job.
By standing on the shoulders of history's innovators and adding their own imagination, determination, and daring, they are taking mountain engineering to unprecedented heights.
You know, if we didn't have this technology and this engineering in place today, we wouldn't all be up here enjoying the mountains. We'd be in the valley looking up going, wow, I wish I could be up there.
And making the impossible possible.